Welcome back, students. Today we're going to look at trees and some properties of trees, as well as something called spanning trees. So today's going to be a lot of vocab. All right, the reason why we're studying trees is because you're going to continue to use trees throughout the rest of the school year, especially when we talk about probability. I think you're going to find the easiest way to look at some probability problems will be to make trees. All right, so we're just going to get a little bit into the background of trees. All right, so the definition of a tree is a connected graph. All right, so that means that there is a way to go from each vertex to the next. So a connected graph with no cycles. All right, so what is a cycle? A cycle, also known as a circuit, is any path that begins and ends at the same vertex and no other vertex is repeated. All right, so we've covered circuits before. Think back to Euler circuits, think back to Hamiltonian circuits. All right, we don't want those. All right, a tree is a connected graph with no circuits or with no cycles. All right, so here we have three diagrams, and let's determine which, if any, are trees. All right, so for the first one, we have a way to go from each vertex to all of the other ones. It does not look like there are any cycles or any circuits in this graph, so that means that this is a tree diagram. For the next one, we can clearly see that all of our vertices are connected. However, we see that from this vertex to this one to this one, there is a cycle. So right here, we have a cycle. Okay, this is not allowed, which means that this is not a tree diagram. All right, for the next one, it first looks like everything is connected. However, take a look right here. We have this vertex that is adjacent to this vertex. I'm going to redraw it off to the side out here, because remember, where I position things doesn't matter. All right, so pretend like this isn't right here. Okay, it's over here now. Now it's very clear to see that there is no edge connecting either of these vertices back to this graph over here. All right, these are not connected. Okay, their edges cross right now, but I could redraw it so they don't cross, and they are not connected because these two vertices, there's no edge going to any of the vertices in this other graph, which means that this graph is not connected, therefore it is not a tree diagram. Next, what we're going to do is we're going to try to draw all of the trees that are possible with 2 to 5 vertices, and I'm giving you a hint that there are 7 total trees. Let's start off with the easiest one. If we have 2 vertices, right now I have 2 vertices, they need to be connected, and so that means all I need to do is draw in an edge connecting the two, and now I have a tree diagram for 2 vertices. All right, a tree for 3 vertices. I have 3 vertices here. Now, it doesn't matter if I just go in a straight line, or if I wanted to, I could make it more in a triangular pattern. Okay, these graphs, while they might not necessarily look the same, they are going to be the same in the fact that I have 3 vertices, and then the middle vertex is going to be adjacent to the other vertices. All right, so here it is right now. Like I said, is more in a triangular pattern. If I wanted to make them all in a straight line, I could. All right, what's important here is that I have 3 vertices and I have just 2 edges, because if I tried to connect these vertices back to each other, then I'd create a cycle, and that would not be a tree. All right, let's look at this next one with 4 vertices. I have this straight line pattern going. I'm going to connect them, connect. All right, now that I have more vertices, it's going to be important to notice the degree of each vertex. This one has degree 1, degree 2, degree 2, degree 1. All right, so it turns out that I could actually rearrange these in a little different way, like this. Okay, here are still 4 vertices, but I could make an edge, make an edge right here. All right, now this vertex has degree 1, this vertex has degree 3, and this vertex degree 1, degree 1. So these 2 graphs are not the same. Why are they not the same? Well, they still use the same number of vertices, which is 4. They still have 1, 2, 3, 1, 2, 3 edges, but the degree of each vertex, all right, the degrees, when we compare degrees, they're different, which means there are 2 ways that I can make a tree diagram with 4 vertices. One where I have degree 1, 2, 2, 1, and another one where I have degree 1, 3, and 1, 1. All right, let's look at five vertices now. So let's do the continue it in the straight line pattern. All right, so this vertex is degree 1, this vertex is degree 2, this vertex is degree 2, and this vertex is degree 2, and this vertex is degree 1. All right, just like this one over here, but now we put on a fifth, and it doesn't matter where we put that on. If we put it on here, if we put it on here, it's going to be the same diagram because the vertices, the number of edges that we have, and their degree of each vertex is going to be the same. So degree 1, degree 3, degree 1, degree 2, degree 1. All right, and then there's actually a third possibility for 5 vertices. If we have 1 in the center and then it's adjacent to all of the other vertices. All right, so something to notice. Okay, this is probably one of the biggest things to notice about these tree diagrams that we just made. For 2 vertices, there's 1 edge. For 3 vertices, there are 2 edges. For 4 vertices, no matter which diagram you look at, okay, there are 3 edges. For 5 vertices, there are 1, 2, 3, 4 edges. 1, 2, 3, 4, 1, 2, 3, 4. All right, which is the first property that I talk about here. Trees always have 1 less edge than their number of vertices. Well, if not, okay, let's go back up to one of these. If I put in another edge, so if I connect this right here, I have now created a cycle, now created a circuit, which means it's not a tree diagram. All right, so this is one of the biggest properties of trees. They always have to have 1 less edge than the number of vertices. So a tree with 100 vertices has 99 edges. If an edge of a tree is removed, it's no longer a tree. All right, so let's go back up here. If I were to remove one of these edges, so let's say I were to get rid of this one, so pretend like this isn't here. Why is this no longer a tree? Well, because this vertex, there's no longer an edge connecting them, which means the tree, it's no longer a tree because it's no longer a connected graph. A tree does not have direction. It can branch upwards like the branches of a real tree or branch downwards like the roots of a real tree. All right, so it's up to you how you draw them, especially when we get into probability. All right, technically, it's up to you. We're probably going to go sideways. We're going to start off with our starting branch, our starting vertex, and then branch off of it that way. But it's up to you because we can go sideways, you can go up, you can go down. Okay, doesn't matter. Trees do not have direction. Here's some vocab associated with trees, right? You do not have to memorize this, but I found it interesting, especially with how much our tree lingo relates to real lingo with trees. All right, so the root is the topmost vertex of a tree. A descendant is a vertex that is farther away from the root than some other vertex. An ancestor is any root between a vertex and the root, including the root. All right, so think about family trees. That's what I always think of when it comes to this unit or to this section in the material. A sibling or vertices that share the same parent. A parent is a vertex that is close to the root vertex by 1 edge. A terminal vertex is a vertex without any children. Internal vertex, a vertex that has children. Height is the number of edges traversed to get to the most distant vertex. Forest is a set of trees, and a leaf is a vertex of degree 1 in a tree. All right. So again, you don't have to have that memorized. I just included it because I found it interesting. So you can pause the video and read through it a little bit more. I went through that very fast. All right, but there's a lot of terminology there that you'd think of, especially when you think of a family tree. Spanning tree. Okay, so a kind of tree that we're going to study. A spanning tree is a tree that contains all of the vertices and some of the edges in a connected graph. The graph has to be connected or else it isn't a tree. And remember that trees can't have any cycles. All right, so what we're going to do is we're going to look at graphs. Okay, we're going to look at connected graphs. And we are going to then find a spanning tree within that graph. So here's a graph right here. This is a K3 graph. Right, K3 complete graph, remember, because this vertex is adjacent to this one, and so on. All right, so this is a complete graph. Right now, this is not a tree. Why is it not a tree? Well, because there is a cycle right here. All right, but what we can do is we can find all of the spanning trees that exist within it. All right, so what that means is we're just going to use all of the vertices, but we're not going to use all of the edges. And so there are three possibilities. We could exclude this edge and get this spanning tree. We could exclude this edge and get this spanning tree, or exclude this edge and get this spanning tree. All right, so properties of spanning trees. If there are V vertices in the graph, then there are V to the V minus 2 spanning trees. All right, that means if you're asked to find a spanning tree, it's not unique. All right, which means that if you look at an answer key, my answer key might be a little bit different than your answer key because you might have found a different spanning tree, and that is okay. All right, so for this graph up here, there are three vertices. So 3 to the 3 minus 2, well, 3 minus 2 is 1, 3 to the first power is 3. That's why there are three spanning trees. All right, so of course, there's been a mathematician before you that has come up with an algorithm for finding a spanning tree. So step number 1 is pick a starting vertex, does not matter which one, label it with a 0. Find all vertices that are adjacent to S and label them with a 1. For each vertex labeled with a 1, find an edge that connects it with the vertex labeled 0. Darken those edges. Look for unlabeled vertices adjacent to those labeled with 1 and label them 2. For each vertex labeled 2, find an edge that connects it with a vertex labeled 1. Darken that edge. If more than one edge exists, choose arbitrarily. Do not use the multiple edges because that will create cycles within your tree. Also, a thing to remember is anytime you have a tree, the number of vertices that you have, the number of edges will always be one less. So let's look at a couple of examples. All right, so this first example has 6 vertices, which means that by the time that I'm done with this, my spanning tree should still have 6 vertices, but it should only have 5 edges. So what I'm going to do is I'm going to pick a vertex to start off with. It doesn't matter which one. I'm pretty boring. I'm going to start with A because that seems like a very good place to start. All right, and then any vertex that's adjacent to it, so A is adjacent to B and C, I'm going to label those with a 1. All right, and then any vertex that was just labeled with 1, I'm going to find an edge that connects the 1 back to the 0. If there's multiple, I just choose one of them, and I choose them arbitrarily. This one, I don't have any options, so I choose this one. Same with this, I need to connect all zeros to 1s, so I'm going to connect right here. All right, and then I'm going to look at my vertices labeled with 1, and any vertex that's adjacent to a vertex with 1, I'm going to label with a 2. So D, I'm going to label with a 2. E, I'm going to label with a 2. All right, so now I need to connect 1s to 2s. All right, so I can connect B to D right there, use that edge. Now I have options. I can either go B to E, I could go C to E, but I can't choose both because if I do both, now I have myself a cycle, a circuit. I'm not allowed to do that for a tree. So choose one of them, connect a 1 to a 2. All right, and then here is another vertex not yet labeled. It's adjacent to both D and E, so I'm going to label it with a 3, and then just choose, connect a 2 to a 3, doesn't matter which one, connect them, and there we go. There we have ourselves a spanning tree. Here's what it looks like not on the graph. All right, so it has 1, 2, 3, 4, 5, 6 vertices still, but now only 1, 2, 3, 4, 5 edges. This is not unique. I had options here. In fact, how many spanning trees could I have made from this? Well, there were 6 vertices, and 6 to the 6 minus 2, which would be 6 to the 4th, I'd use a calculator here, and that gives me 1,296 ways to make a spanning tree. All right, so here is one way that I made a spanning tree out of this graph that had 6 vertices. This next graph looks like a mess, okay, but that's okay. We can work with it. It's not going to be too bad at all. Finding spanning trees is very simple. We connect numbers to the next number up. That's it. All right, so pick any vertex that you want to start off with, and I'm going to start off with vertex A once again, so I'm going to call it 0. A is adjacent to B and E, so I'm going to go ahead and label those both with 1s. And then I need to connect 0 to 1. So I'm going to darken this edge. I'm going to darken this edge. All right, and then I'm going to label any vertex that's adjacent to a 1 with a 2. So B is adjacent to G, so I'm going to label it with a 2. E is adjacent to D. It's adjacent to F, and it's adjacent to I. All right, so now I need to connect the 1s to 2s. So I'm going to connect 1 to 2 here. Kind of looks like I have a cycle, but remember there's no vertex here, so I could redraw this out. I can make it planar, or at least this part of the graph planar, and that means that it would not actually be a cycle. All right, and then connect this 1 to 2, connect this 1 to 2, and connect this 1 to 2. All right, and then H isn't yet labeled. It's adjacent to a 2, so I'm going to label it with a 3. C is adjacent to a 2, so I'm going to label it with a 3. Now I have lots of options here. Just choose one. All right, so I could go G to H. I could also go G to C. All right, there we go. Now I have gotten to all of my vertices. So now what I'm going to do is I'm going to redraw this out because right now it looks like a mess. All right, so what I have here is my spanning tree all drawn out. I have now adjacent to B and E, so A to B and E. B did to G and then branched off to H and C. So B goes to G and then branches off to H and C. And then it terminates there, terminates here. And then E, okay, E, I had it adjacent to D, I, and F. So branches out to D, I, and F. And then each of those were terminating vertices. All right, so that was 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices, which means my number of edges was 1, 2, 3, 4, 5, 6, 7, 8. All right, and that is your vocab, your notes for trees, as well as spanning trees.